The pleasure to have Johannes Hoffmann-Madrenas from Weizmann. Most of you have probably already met him. So Johannes got his PhD working with Dr. Assaf at Würzburg, which is one of the world's leading groups doing on Monte Carlo. And Johannes is actually one of the leading figures now in doing on Monte Carlo in electronic systems, to the extent that he's actually one of the people who came up with this open source package that many people use called ALF, which he'll probably tell us about a little bit. And so now he's a postdoc at Weizmann since 2019, working with Harrisburg, and it's been a great pleasure collaborating with him, actually, right from the beginning of this postdoc. So, Johannes.
Thank you, Devanjan, for the nice introduction. And today I want to present work that I've actually done in collaboration with him and Eris. And I will be talking about superconductivity, charge density wave, and supersolidity that can arise in flat electronic bands due to a non-trivial quantum metric. Okay, there is a time delay. Right, so this whole line of research was motivated by the discovery of superconductivity in twisted bilayer graphene, where on the left-hand side here, I plot a schematic band structure as a function of energy in the Bringas zone. And I don't want to go into too much detail because the main takeaway message from this figure is that you have density of states, lots of it in a flat band close to the Fermi level. And experimentally, you can find a superconducting phase depending on your carrier density, of course, at low temperatures. And this was motivating us to look into flat band superconductivity in more general terms. So this talk is not aiming at describing twisted bilayer graphene and all the details, but it's really to understand how superconductivity can arise in flat band systems. And this is kind of peculiar because typically, if you want to have superconductivity, you have to manage two different energy scales. On one hand, you have to pair two electrons into the Cooper pair, which can then condense to give rise to superconductivity. So there's one energy scale given by U, the effective pairing energy, but you also have to make sure that these Cooper pairs can form a coherent state over long distances. So the second energy scale is the phase coherence, and typically those two energy scales compete with each other. So for example, if I take the attractive Hubbard model as one of the maybe most famous models in condensed matter physics, if I start at weak coupling, where the coupling constant is smaller than the bandwidth W, this theory is well described by BCS, and I have a temperature scale that is exponentially decaying with weak interactions. So here I'm essentially limited by the pair binding energy. Then you would think if I increase the interaction strength more and more to get easier, to have an easier time to form the Cooper pairs, TC should go up. But then at some point I reach a maximum before the critical temperature is decaying again, because now the limiting factor is not the binding energy of the Cooper pairs, but rather the phase coherence. So I'm essentially, I can treat the bandwidth almost as zero, or at least as a small perturbation. So I'm localizing the electrons. They can't move, and they don't have a means to establish the phase coherence over long distances. So from that perspective, it's actually quite interesting that you can find superconductivity in almost flat bands. So now let's take a step a little bit away from twisted bilayer graphene and ask a more general question. And that is, what is the ground state of a system where I have a flat band around the Fermi surface, or almost flat bands, which is then separated by an energy gap from either conduction bands or valence bands? Can I find superconductivity in there? And if so, is this a robust phase? Or are there additional competing phases? Right. And if I have more than one possible ground state, then what determines the competition between the different phases?
I have a question regarding.
Sure.
And one more backwards. Yeah, so I understand that in the Hubbard model, probably there's some constraint. If you have large U, these stuff, even though they form pair, they don't fall
Yeah.
as much. That's if I assume that there is already some intrinsic full fermion interaction term that looks like a pair hopping. If they're already there, then I guess I'm not necessarily going to experience this substitution.
Yes, and we will see this later on. Right. Yeah, so if you manually build in pair hopping, then yes, you will have a mechanism to generate phase coherence.
Okay.
Right. So, but then some of these bands where have the flat or some of these flat bands are special, namely in the sense that kind of answering already your question. That even if I have local electrons or localized electrons due to the flatness of the band, the Cooper pair can still delocalize in the sense that I can have a Cooper pair hopping to nearest neighbor sites. And if this is the case, then the interaction strength is pretty much the only energy scale that I have in the system. So the critical temperature kind of has to be linear in U, which is quite different from either the exponential decay at small couple or at weak coupling, or the 1/U behavior at strong coupling in the Hubbard model. So in which sense are they special? The first attempt that we were looking at was we were considering topological flat bands in the sense that there's a finite Chern number. And we have done two different simulations. On one hand, we have a simulation where the lower band, so this is a 2-orbital system. I have two bands, one is centered around -2, the other one around +2. And compared to the gap between those two bands, the dispersion is already kind of flat, but not yet super flat. And we will be interested in a regime where the lower band is around half filled, so quarter filling overall. But then we found a way how we can make the dispersion of the lower band even flatter. So to be more precisely, that the width of the lower band compared to the gap between those two is almost a factor of 100. And we were looking at this using the quantum Monte Carlo technique that Debanjan mentioned, built into this package of ALF. And we extracted the superconducting temperature. Let's first look at this inset here. The solid line is the data for the more dispersive band, while the dashed line are the results for the flat band. And we indeed find a fairly large regime in the Hubbard interaction U between 1 and 4, where for the flat band, we have almost perfect linear scaling of TC with the interaction. And then around U, we reach the energy gap between those two. So the interaction would be able to excite states from the lower band into the higher conduction band.
The units on the two plots the same as in for measured in terms of T.
Yes.
You take the entire model. So
Yes. So for the Monte Carlo, I'm always simulating the entire model.
there's no whatever band projection.
No, there is no band projection. I will later on use band projection, but not for the Monte Carlo side of things, but more to get an understanding of where does the physics come from, and also to derive where does the pair hopping terms that you mentioned earlier are coming from, originating from. And then in this setup here, there is actually a second temperature scale plotted in red. And this is the temperature where, since we are looking at attractive Hubbard interaction, where the spin fluctuations start to freeze out because the temperature is below the spin excitation gap. So what this means is that this superconductivity actually is not really originating from a Fermi liquid, but rather from an incoherent charge fluctuating state. And actually, there have been, so on one hand, we found in a numerical unbiased way that you can find superconductivity in a flat band, at least if it has a topological invariant. But then there is also a strong fluctuation regime. The spin fluctuations are gapped out and frozen out. But here I'm plotting the inverse susceptibility for pair fluctuations and for density fluctuations. So having small numbers means I have a lot of fluctuations going on. And then when I zoom in, especially for the dashed lines, here the two curves are very, very similar. And this can actually be understood by an approximate effective SU2 symmetry. So if I had an SU2 symmetry, in this case, the two pair and charge excitation would be identical and related by symmetry. And it's the finite bandwidth to the second band which breaks this SU2 symmetry. And only when I enter the superconducting regime, the charge fluctuation saturates and doesn't diverge as well. So it's a very close competition between charge instabilities and pair fluctuations or superconductivity. And it's so, the competition is so close that if I turn on a fairly weak nearest neighbor attraction, I can tip the scales such that the two susceptibilities cross, and in the end, the charge susceptibility diverges faster than the pair fluctuations, and this triggers in phase separation. So the system either wants to add electrons and completely fill the flat band, or to remove electrons and make it completely empty. If it's constrained, then you would divide the sample into two halves. One is where the lower band is completely full, the other one where the lower band is completely empty. So this was then setting up the key questions of this project. And that is, first of all, do I really need the non-trivial topology of the flat band, or can we also have the same or similar physics in trivial flat bands? Then are those two states the only competing states, or is there more? Then for a topological band, we know that the Wannier states have a power law tail, so they are not really exponentially localized. So how important is the role of the localizability of those Wannier states that span the flat band? Could, for example, the interaction give rise to a finite dispersion, so that I had electronic bands that were originally flat, but now, due to correlation effects, the electrons can start hopping themselves? And is there a limit where we can gain more insight than just deriving numerical data? So with this in mind, we designed a new model where the key feature is that I have on one hand a tuning parameter that we call zeta for the kinetic energy or Hamiltonian. This is the non-interacting part, which was designed such that on one hand, the Berry curvature vanishes identically. So there is no topology, no churn index, none whatsoever. But still, with this parameter zeta, we can control the extent of the Wannier function spanning this lower band. But still, when I set zeta to 0, I can derive a decoupled kind of atomic limit where I can get an analytic intuition of what's happening. And the model is given here. So the kinetic term, I have the tau Pauli matrices that act on the orbitals, and I have designed them to be sine alpha plus cosine, or alpha, such that I really have a dispersion at energies plus and minus 1. So it's a perfectly flat band. And this zeta controls the extent how much alpha is varying. If I send zeta to 0, alpha is 0. So only the cosine survives. The sine is 0, but there is no more momentum dependence. So in that sense, I have an atomic limit that everything happens on site. And as an interaction, I have the Hubbard interaction, again, attractive to form Cooper pairs. And I may or may not turn on nearest neighbor repulsion. And this setup, specifically the small theta parameter, allows us to derive an effective Hamiltonian. So this is a fairly busy slide. Let me walk you through this here. The first thing is we can analytically calculate the wave function. So what I'm showing here is in one of the orbitals, the wave function itself, so not the absolute value. So I can still know the phase relation between the wave function. It's an orbital that is centered around R0, and then it exponentially decays with zeta, indicated by the size of the wave functions. When I now take the original Hubbard interaction and express this in terms of the creation operator for these Wannier states that span the low band, the most important contribution that I get is when all indices always look at the center of the Wannier orbital, or in other words, I will reproduce the Hubbard interaction with an effective strength that is proportional to the wave function amplitude at its center of the Wannier state. And
When you say breaks the time resistance, I see red, not orange. So maybe
does it break time reversal?
you have another no time. So
No, it does not.
It's another layer, right? This is only showing the one
Yes.
for one of the.
Right. This is the state for spin up. The orange dots are super small and hiding here. So this is order 1 in theta. This is order like linear in theta, quadratic in theta, and the third power in theta. And the spin down state will have the complex conjugate wave function. So there is still time reversal symmetry.
the time versus symmetric, but you do have an explicit spin orbit count. That makes sense?
Where do you see the spin orbit coupling?
There is no such Wannier wave function for the spin down component.
No, I will have.
I can replace the red with the orange.
Yes.
With the red and flip the spin.
Yes. Yes. So you still have the relation that the wave function of the spin up complex conjugated is the wave function of the spin down.
Correct. Yeah.
So this. Yeah. Yes. No, there is no SU2. Actually, there was no SU2 from the beginning, because if I go back here, we changed the sign of this hopping according to the spin, so there was only a U1 symmetry in spin.
I see.
Because we wanted to have time reversal symmetry, otherwise we would suffer from the sign problem in the Monte Carlo simulations. Right. So after sorting these terms to find the leading contribution as the Hubbard interaction, I also know that at least in the limit where theta is 0, all of the other contributions actually vanish exactly. And I'm left with a Hilbert space in the flat, or Fock space in the flat band, where I want the local Wannier orbitals either to be empty or double occupied. Otherwise, I have to pay an energy for the Hubbard interaction. And this justifies why later on I will only focus on charge degrees of freedom and ignore spin degrees of freedom, sorting the other terms. And these come about at leading order or in quadratic order in theta, the first correction for finite theta values that I can pick up. And since the orbital is not perfectly localized in one unit cell, there is a chance that I can create a state here, say, but using the creation operator from the neighboring site. And if I sort them right, then I have the pair hopping terms by eta x, eta y. But there are also density-density interaction. And due to the originally broken SU2 symmetry, you will also here only see the U1 symmetry. So this is why this mainly maps to an XXC model in the charge sector, in these pseudospins where the pseudospin is the charge degree of freedom. And I will come back to this correlated pair hopping term, or this correlated hopping term later on. I mentioned this here completely for completeness sake, where density fluctuations can allow electrons to hop between neighboring sites. So one of the assumptions in this derivation was that I can assume the spin degrees of freedom have frozen out, and I'm only looking at the charge sector. So we went ahead and tested this by looking at the spin susceptibility. And this solid line here is the spin susceptibility that I get from a single-side Hubbard model, or two-side Hubbard model, actually. And this charge gap, or the spin gap, sits at U/4, I believe. So you can really see that even for interactions, the charge degrees of freedom gap out, and I'm only left with charge excitations. Sorry, I think spin gaps out. I don't know if I said spin. Then we continue a similar analysis and extract the superconducting TC, which is happening at temperatures, notice the 10 to the -2 around here. So really at the superconducting transition, there are no charge fluctuations. And we see again that the TC is almost linear in U, which also makes sense because if I go back to this slide with the hopping term, then really once I've projected onto the charge degrees of freedom, the only parameters in the Hamiltonian are J perp and Jz, and both are proportional to U. So again, U is the main energy scale at this stage. And yes. For the first simulation, V is set to 0, but V would be the nearest neighbor interaction.
Oh, I mainly wanted to see if you could go to a regime where it looks like an anti-ferromagnetic coupling.
Yes, so that's actually a good point. So while it's a little bit trickier to tune the sign of J perp, and J perp turned out to be ferromagnetic, which is giving rise to the superconductivity. If I have the in-plane order of these pseudospins, I can tune the out-of-plane component. I can tune this from ferromagnetism to antiferromagnetism, and we'll see this later in the talk. One more thing that I wanted to say here: the other feature of this effective Hamiltonian is that the two coupling strengths J perp and Jz are both proportional to theta squared, which essentially comes about that I either need the product of two matrix elements like this, or the product of two matrix elements like this. And then I get always either a theta times theta or a theta squared contribution. So this is directly related to the geometry of the band, or the width of the wave function, that then controls these effective hopping parameters or coupling parameters. And rescaling TC by this theta gives an almost or a fairly nice data collapse, even though we didn't tune anything here. But this essentially confirms that TC really scales like theta squared times U. Before, we have already seen that the charge susceptibility, the charge susceptibility can also diverge, and we see similar features here. So when we lower the temperature, the charge susceptibility grows and grows and grows, and then it only starts saturating at a fairly high level when we enter the superconducting regime. Notice that both scales are on a logarithmic plot. So we have again the competition with the charge fluctuations. And this time, coming back to your question, we are not interested in attractive nearest neighbor, but repulsive nearest neighbor, which here will tune the out-of-plane component to the antiferromagnetic regime. And if I have antiferromagnetic coupling between these pseudospins in the z direction, I essentially trigger a charge density wave. Because it's the pseudospin, so it's the charge relative to one that we are measuring with this eta c.
Can you get a pair density wave this way? Maybe help us.
So, well, I don't know if we wanted this, but no, we don't see a pair density wave.
Charge density wave or superconducting.
But by pair density wave, if you mean,
FFL.
yes, we get it.
Well, okay, what do you mean by pair density wave? I was thinking of these FFLO states where you have pairing with finite Cooper pair momentum.
Yeah.
This we don't see.
Great. But what do you mean by super solid?
We will come to this later.
Something that's both a CDW and a superconductor or a superfluid.
Okay, so I was, when you asked for finite momentum, I thought you were referring to a translational symmetry breaking by the ordering, like the superconducting ordering parameter itself.
Yeah,
This
basically all-side pairing, right? And if that looks like a boson and orders at finite momentum.
yes.
This is not a, can I not call it? I mean, okay, I don't know. There's a huge history to super solid.
Yeah. 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 So okay. So the definition of super solidity that we will be having here is really you have the coexistence of a charge density wave and superconductivity. And the superconductor is the conventional K minus K pair. So the Cooper pair itself does not carry momentum, finite momentum. But the finite momentum or the breaking of translational symmetry is given by the charge density wave. Yeah.
Can one estimate how costly these FFL states are?
Sorry?
Can one estimate how costly these FFL states are?
It's difficult to estimate how costly they are. What I can tell you is that an instability typically shows up as an enhancement of the pair correlation function. And the divergence speed or the enhancement is related to the energy gap and when it saturates. And here we didn't see any enhancement or any scaling with system size at finite momentum for the pair energy. So from that estimate, I would say it's a fairly high energy, but I can't tell you how high. So it's high enough that it doesn't determine or show up in the low energy fluctuations. Yes. Right. So when I have the regime where the correlation length increases with system size, I'm in the ordered phase. So here I'm looking at the charge correlation, the charge density wave correlation length in units of the linear system size. And this crossing point here is from the RG perspective, defining the critical temperature for the charge density wave. This was exactly at quarter filling with one electron in the flat band. We can look at this as a function of density and track the critical temperature. Now, only at quarter filling, the charge density wave is commensurate in an insulating phase. If I have excess carriers or lack thereof, like additional holes or electrons, then when we lower the temperature further, we find a second transition where we generate superconductivity on top of the charge density wave. So the charge density wave pattern survives, but now we have additional superconductivity. And the temperature decreases with density if I approach density of quarter filling. So in our interpretation, what we really think of, you have this, it's easier to think of additional electron doping, so on slightly this doped side, where you have the localized charge density wave pattern, and then you have Cooper pairs that hop in the background of the charge density wave. And when the temperature is cold enough, these additional carrier can condense and form long-range phase coherence. And if I go towards zero temperature, then there are no charge carriers, and it remains an insulating phase down to zero. And we extracted this super solid phase by analyzing the superfluid stiffness, in this case for a fixed temperature, as a function of density. And the BKT criterion determines when the BKT phase sets in. So the crossing point of these stiffness data with the BKT criterion defines essentially the critical filling, which are these data points here.
So this is a bit different from what I mean, when I say PD term.
Yeah, yes. So I thought you were thinking of a pair density wave, and we are not seeing a pair density wave.
So just to confirm, the super solid has the exact same periodicity as the super.
Yes, we only see any translational symmetry breaking at pi, which is the wave ordering vector for the commensurate charge density wave.
Yeah, because had it been real PDW, we can actually go into a CDW, but the periodicity will not change. Like this vestigial order.
But it depends, right? If you have a uniform superconductor around as well.
Oh, well, then you need a two component, well, it's a more complicated story.
Right, that's why when you said PDW, I was like, what do you mean? PDW?
Yeah, I was just thinking of a single momentum PDW, but
Right,
maybe.
without any other uniform superconductor.
Yes, if
right.
there's no uniform component,
Then you're right.
you would have a, I don't know, like a four fermion thing that still breaks translation, but.
Right.
Breaking one
Yeah.
and would have a different.
Yes. So this now sets the state to look at the dynamics. So we are looking, let's first look at the top left corner, where we are presenting the excitation spectrum for the single fermion excitations. And the zero energy sits here. We are walking through the high symmetry path in the Brillouin zone. So essentially this triangle from 0, 0 to 0 pi to pi and back. And these dashed lines in the stark red, they indicate the position of the non-interacting flat band. Here, it's actually having a finite dispersion because we truncated the hopping terms. But this should not matter at all for the numerics, because this is an effect at theta to the fourth, while the rest is theta squared. Right. So this shaded area at the high energies is the conduction electron excitations at around 2 as an energy. And then here we have split the conduction electrons into, if it was repulsive interaction, you would call them Hubbard bands. But here you have these strongly correlated preformed Cooper pair bands. In the pair excitation, we see that we can have gapless pair excitations at Q equals 0 in line with a superconductor. And there is again an approximate SU2 symmetry, which almost relates the pair excitations with the density excitations. And this is why the dispersion in those two figures are the same. And also in a superconductor, you have a gapless charge sector. Right. This is for zero nearest neighbor interactions. Then we can turn on the nearest neighbor interactions and go into the charge density wave. And suddenly the high energy part of the spectrum looks very similar, but the low energy spectrum developed a dispersion. I will explain this in a second in more detail, but before doing so, in this case, the the pair spectrum is gapped. So I have low pair excitations because of the strong attractive Hubbard interaction, but they haven't condensed at this point. I'm in the CDW phase. But in contrast, I see this central peak at the pi point, indicating the charge density wave. So where does this dispersion come from? And here we have to look again at the wave function, or at this sketch of the wave functions and the different terms in the Hamiltonian. And more specifically about this pair hopping term, or not pair hopping term, sorry, for the density assisted electron hopping term. So it's maybe a little bit difficult to see, but there are those two dots which indicate the position of the pair or the density fluctuations, and then the line are the fermion hopping terms. So a fermion can hop from here to there depending on the density at this blue side, but also if I rotate this bond to here, a fermion can also hop from here to there depending on the density there. The difference is, though, here I'm multiplying a plus with a minus, so this comes with a relative minus sign, while here, since one is the Degard operator, I have to include a complex conjugation, so I have I times minus I, so it's plus again, which means if an electron hops from this red side to that red side, it depends on the density on those four sides, but it's plus on these two and minus on those two. So this electron hopping really is sensitive to the charge density wave fluctuations. And if I assume or replace the density operator by the expectation value of the charge density order parameter, then I get this dispersion, which is the orange dashed line. So this density assisted electron hopping in the charge density wave very nicely explains the dispersive conduction electrons. There's one thing that is peculiar here, because you should really think of these two bands as starting from the correlated bands where you add a dispersion on top. Which means, in other words, if you make the charge density wave order parameter larger and larger and larger, you are increasing the bandwidth more and more and more until there is a point where you may even close the fermion excitation gap at the gamma or M point. Because what this, like, to get a physical intuition of what's happening there, when I create an electron in the background of the charge density wave, I have to pay two energies. I have to pay the Hubbard interaction because it's an unpaired electron, and I also create a defect in the charge density wave. But on the other hand, this density-assisted hopping allows the electrons to delocalize and gain from kinetic energy. And now it's up to the balance between the Hubbard and like defect energy compared to the kinetic energy, and they in general could cancel if delta goes large. So this asks the question, does this really happen? Like, this is super, it was unexpected to us, because usually when you go deep into a phase, you increase the gap, you don't close the gap. And you don't want to generate a Fermi surface at low temperatures deep in a phase. So we are now tracking not the temperature, but the width of the Wannier orbitals, which also determines the kinetic energy. And we are keeping track of the single particle energy. So this is really the value at the gamma point as a function of theta. And we do see that the gap closes, or the gap is reducing, but then it remains finite, even if we crank up theta to more than 0.8. This dashed line here is an analytic expectation that I have without any parameters, just starting from this theta equals 0 limit. where I only have density operators and every operator in the Hamiltonian commutes. So it's actually quite easy to estimate this. And then at the same time, when I increase theta more and more or make the Wannier orbitals larger and larger, the charge density wave order parameter, which is plotted here, at some point starts to reduce. But it remains finite even if I go to theta of 1. And the last quantity that we plot here as these axes, that's the pair gap. And we can track the position in theta when this pair gap closes, which would likely indicate superconductivity. Even though the superconductivity is generated at without killing the charge density wave, and we were at commensurate filling of 1. So we are looking at the insulating charge density wave, and all we do is we make the Wannier orbitals thicker and thicker, larger and larger. And indeed, this is exactly what happens. So we are looking or plotting here the correlation lengths of the superconducting fluctuations, essentially the coherence length. And since as for 4 different system sizes, and as the fermions remain gapped all throughout, one should expect a 3D XY universality class. XY because we are breaking U1 and we are looking at 0 temperature of a two-dimensional lattice. So it's the 3-dimensional XY universality class. And the critical exponents are known. And indeed, we can do a data collapse of those 3 terms if we rescale the theta parameter and the temperature according to the RG transformation rules. And yeah, how am I doing in time? This would be a point to stop, or 4 more slides?
Definitely have more time.
Okay. So now before summarizing, let's discuss the results that we have found here a little bit more. So there have been various proposals how you can bound TC, sometimes from below, sometimes from above. For example, this list is by no means complete. But for example, there is a bound on the superfluid stiffness, which in turn then determines the superconducting phase by applying the optical sum rule to the current spectrum. If this is done correctly, then this is indeed a proper bound, but one has to be careful in applying it appropriately. Yes. So essentially what I'm saying is one has to be careful that one projects either correctly projects it to the flat band, and then it's fine to look at the excitation or the optical sum rule and the current carried by the low energy degrees of freedom, or one doesn't project it, but then one should include all bands, which typically leads to a very large bound. And also this work led to a interpretation of the bound, which is correct, that TC is lower than the Fermi energy below divided by 8, if one assumes one has a single band, spin degenerate, of course, with a parabolic dispersion. So it's not a generic bound that TC is smaller than EF. It's a bound at TC only in the setup of a parabolic band. And here I want now to use our results to argue that there is actually no fundamental bound on TC, at least in units of the Fermi energy. So one definition of the Fermi energy is generated by looking at the density of states. Here, this is the density of states of the interacting system, where I have the energy on the y-axis and then the density of state on the x-axis for some given filling where there is some active band that is partially filled, or like multiple bands that cross. So there's one blob in the density of states where I have a partial filling. And now you can think of applying a gate to the system or change the chemical potential until you reach an insulating state. You deplete electrons until you reached an insulating state. And since this is an interacting system, the shape of the density of states does not have to remain fixed. It can change as a function of filling. And then you can take the difference of those two values for the chemical potential and use this as your definition for the Fermi energy. A similar approach is you take again the same insulating reference state, determine this density of states, for example, by doing SDM tunneling experiment at a very low rate, so that you essentially extract the electrons that tunnel in before the second electron is tunneling between the tip and the sample. So you see the non-interacting density of states with respect to this insulating phase. And then you can simply fill up this density of states until you have reached the same number of particles that you originally wanted to. This is essentially what you do in textbook physics, Introduction to Condensed Matter theory, when you look at non-interacting Fermi liquids. And this would be your second definition of the Fermi energy. Without going into the details too much, let me maybe explain this side a little bit more. In our model, we had, when we tune the system to hit this insulator, there is no second band. So this is really the completely empty system, the vacuum. And if I now want to know what are the energies to bring in a single electron, this is the non-interacting dispersion. And if you allow me to again treat all hopping terms or work in momentum space, this band was perfectly flat. It was sine alpha tau x plus cosine alpha tau y was the Hamiltonian. So then obviously putting in n numbers of bands, as long as n is less than filling this band completely, will give rise to a Fermi energy of 0. Yet we had a regime where there was a finite Tc. So if I was to divide Tc by 0, it's infinitely large. So there is no fundamental bound on Tc using this definition of EF. The other definition of EF is a little bit more tricky, but you can also show that the difference of those two energy scales is proportional or is equal to the difference between J-perp and Jz. So the anisotropy of your XXC model. But on the other hand, Tc scales with the strength of the pair hopping with J-perp. And again, J-perp divided by Tc divided by EF can be arbitrarily large. Because you can think of making delta J smaller and smaller and the anisotropy weaker and weaker.
Right, does that mean that if I have delta J equals 0, then there is no interaction value?
Yes, but one has to be a little bit careful with the limit of delta J equals 0, because then I'm recovering an SU2 symmetry, and I can't break
You can't have
superconductivity. So where the logarithm is then taking care of it. So there is the subtle regime on where you can, but in general, J-perp can be larger than delta J. So I have, again, an unbounded critical temperature. Yes. And then also there have been proposals for a lower bound on the superfluid stiffness, where this time it's then given by the band geometry. So I define the, I always confuse this, the quantum geometric tensor. I've given you the definition here, where the minus indicates that I'm only looking at this lower flat band. And this has a real part, which will be the Fubini-Studi metric, while the imaginary part is the well-known Berry curvature. The Berry curvature in our example is always 0, but this object does still have a real part. So the Fubini-Studi matrix is, or metric is not 0, and this essentially measures the extent of the Wannier state. And more precisely, I can take the trace and integrate over momentum, and the result is theta squared by 2. So if this was a lower bound on the superfluid stiffness, I should have a superconductor at low energies. But I've shown you that at least in at filling of 1 electron, exactly at quarter filling, I can have an insulating ground state, which is not a superconductor. So when I talk about lower bounds on the superfluid stiffness, you really have to think about the proper setup and the proper physics at hand. And what are the electrons that actually superconduct? While this theta squared by 2, or is the scale for the TC when we didn't have nearest neighbor interaction, and this effective model was in the easy plane regime, in the easy axis regime where I have the charge density wave, you really should think of the excess carrier around the charge density wave, and then this derivation doesn't apply. So one has to be very careful when one applies lower or upper bounds to the superfluid stiffness. And with this, let me summarize. We have designed a model where the extended Wannier function gives rise to an XXC model with assisted hopping terms. We could use this derivation to explain, on one hand, superconductivity in non-topological bands. We also understand the competition, for example, in this case, with additional charge density wave order, and also how we can get a supersolid, which is the coexistence of charge density wave and superconductivity at finite doping. But even the insulating phase at a commensurate doping of a commensurate filling at quarter filling can be driven into a supersolid, making use of this density assisted hopping term by increasing the Wannier states more and more. And then summarizing the last 2 slides, there is no universal bound on superconductivity. So thank you for your attention.
Any other questions?
I wanted to ask, so in the very first part, you talked about a model which had some topology, right?
Yes.
So was there any effect of topology besides just the extended Wannier functions? Was there some mixing of this? You see the H state that is mixed with some kind of convective excitations.
Can you repeat the last part of your question?
The H state do mix with the Goldson mode or something?
The edge state. Oh, here we are always looking at periodic boundary conditions, so there is no edge state. So the edge state doesn't really mix in the game. From my understanding, at least in the derivation to this low energy effective theory, there should be 2 things that happen. On one hand, in a topological band, the Wannier states are not exponentially decaying, which in other words means for the effective model, I should have interactions that have power law tails. But then if you think about what really drove, at least to leading order, the physics that we saw, this was the overlap between neighboring Wannier states. And topology guarantees that you can't completely localize this. So there is a lower bound on the overlap integral. While even if you have trivial topology, the Wannier state does not necessarily have to be a delta polarization, localization. It can still leak out into neighboring unit cells. It just has to decay exponentially. I'm not sure if we found like deep science of the topology. Maybe Debunjan has another comment on this, but I don't think that the topology is super.
What was the question?
But the topology shows up somehow.
Yeah. The important part is the wave function, the extent of the wave function, that you have a finite extent.
Maybe a follow-up question to that is that, have you done the Chernobyl 1 - 1 calculation with the Milton boundary? Do you see gapless fermions still? Or really as a quadrupole? Well, plus the delta,
Mm-hmm.
the original band structure is kind of, is not completely right.
Mm-hmm. Mm-hmm. To be honest, I haven't thought about it. So there is no, like, one has the time and resources, it would be easy to repeat the calculation. If I have to guess, sure, in this with open boundary conditions, you have the surface state connecting the two bands. But on the other hand, I would claim that the superconductivity, which is mainly a bulk effect originating in the lower bands, may not change all that much.
That means at best you get the chiral split into. If the chiral modes are still there, it doesn't have to remain one short mode.
Yeah. Yeah, but also, so if I go back here, maybe. So the surface state would primarily connect the two like dotted bands. Now, when I start splitting the single band into the like correlated bands, I'm not sure if I would necessarily expect the Majoran, like another edge state between those bands.
Within those videos.
So I don't know how important the additional state that I have here is to the physics that I find there. So I think I should still find the superconductivity just because the bulk is so much larger and I have so much more degrees of freedom there. What exactly happens to the edge, I can't tell.
Perhaps we could think of a two-stage transition. There's a CW that is going to come in anyway first. Talking about a super solid.
Yeah.
After that, there's going to be some kind of an extra band coming out, and whatever it comes up with. So
Yeah.
it could be merged in one of these new bands. It could be a new band. Apology, and you're back to
Yeah.
the story without your number. I mean,
Yeah. Yeah, it would be an interesting point to look at, but I can't give a more precise answer at this point. Any more questions?
Maybe I'll just comment. I mean, I know you were trying to go back to our original title and being a little cheeky, but superconductivity is not truly boundless, even at low energies, which is the kind of the point of my recent paper with Dan.
Yeah.
your paper called superconductivity is bound.
Yeah, I know. So that paper too. All that. Yeah,
Yes.
just to set the record straight.
Yes. Yeah, no, if you apply the bounds on the superfluid stiffness correctly and you do the right gauge coupling, then there is a bound on the superfluid stiffness originating from the optical sum rule. And once done correctly, this is a rigorous bound and therefore it's a rigorous bound on TC. Yeah, so without any further restrictions, yes, there are bounds. If you ask, is there a bound on TC over EF, then there is none.
Right, if there are no other questions, then
Actually,
oh,
sorry.
go ahead, no, go ahead.
Normally we don't worry about this, but since it seems like you're getting a lot of information from the phases of the body state, I may ask, the choice of running state is depending. It's state dependent state.
Yes.
So you could make it bigger, smaller, potentially I could also change. I understand that for practical purpose, everybody would go for the minimally localized thing, and that totally makes sense. to me.
Yeah.
But.
Yeah.
How do I know if I take a volume wave function and try to rethink about that?
Yeah, no, it's definitely correct that the one-year state or the one-year wave function itself is not unique.
Wait, what
The
question? I heard a lot of statements. What was the question? I
The
missed that.
question is that it seems like a lot of the analysis depends on where, what phase the one wave function gives at a certain location, like nearest neighbor, second nearest neighbor, right? Like it has these.
In this,
the blue and the red.
for the analytical expansion, you mean, in powers of zeta?
yes,
Yeah.
That's right.
Yeah.
So supposedly we change we use a possibly terrible gauge for the Vanni state. I could have a pretty ugly looking Vanni wave function. And it would change a lot of parameters. Maybe changing parameters is not that much of an issue, but I presume you want the red dots to be red dots, green dots to be
Well,
green dots. And
well, actually, so so to some extent, yes and no. It's not that the wave function, like this is a neat picture where it's easy to derive this, but at the end of the day, I think you can write all of these terms as overlap integrals between one-year states.
that's totally fine. But it would depend on the choice. Somehow, I'm just saying that somehow there's some nice choice, and if you're somebody smart enough to make the right choice, then some structure becomes clear, and for some unfortunate person who picked the
Yeah.
wrong page, then that person will suffer. Right.
Yeah.
So, sorry, go ahead. No, it's your talk. Go ahead first.
Yeah. So in quite a few of these bound papers, you then connect the degrees of freedom with the projection operators onto the flat bands in a fashion where this is essentially your central quantity, but this is then the geometric tensor itself is still sensitive to the gauge, but the trace is not. So the object that you have here is then gauge invariant, so it doesn't dementor. Yes.
Over here it is, but this,
Yes.
this parameter, if I remember correctly, this tells you that if you choose the minimally localized Vanni state, this is the lower bound to that.
Yeah.
Sign, but.
Yeah.
I think that terrible choice, I could make it big.
Yeah. Yeah, I don't have a good answer for you. So, Devanshan, do you wanted to comment?
I was just going to say a minor thing. So I think ultimately for everything, and in as far as superconductivity is concerned, you really want to study its electromagnetic response. And it's like the transverse current correlation function. So you have to basically do some kind of minimal coupling, but you have to know how to couple the vector potential.
Yeah.
So I think at least for trivial bands, I think we understand that you should really be working with the maximally localized one-year functions. But for
Should, in what sense? It's should means more convenient.
well, that's the regime where the naive gauge, naive coupling to the vector potential, meaning you just do some kind of a pulse type substitution, makes sense. But I don't have a good answer for topological bands on what, whether which choice of the one-year function gives you the best understanding of what the low energy physics is.
But it seems that you're suggesting that had I mess up the Vanni state, meaning not making it maximum localized.
Yeah.
The minimum coupling is just false.
No, the naive minimal coupling, where you imagine writing down some projected model and just do a simple part substitution.
Right.
Yes, you can run into difficulties. That is not what will determine your true low energy electromagnetic response.
And I understand generically this may leads to ambiguity, but would they all have the same answer if I just take the cube root zero limit?
So a projected gauge transformation versus this naive gauge transformation will not have the same answer.
Well, but I'm asking for some measurable quantity at cube.
So it's a measurable quantity, the right way of doing it is to use the projected gauge transformation, and that will give you the physical correct answer. All right, are there any other urgent questions? Given that it is Johannes's last day here. Okay, if not, let's just thank Johannes one more time.